Hello, everyone. Welcome to our podcast, where we dive deep into the latest research papers in AI and machine learning. Today, we're reviewing a fascinating paper titled, Maybe Only 0.5% Data is Needed, a preliminary exploration of low training data instruction tuning. Are you ready to get started?
Absolutely. This paper is from a team at Zhejiang University and Zhonghao Xingying Technology. The main focus is on instruction tuning for large language models, or LLMs, and how we might drastically reduce the amount of data needed for effective tuning. That's a hot topic these days, isn't it?
It really is. With the explosion of LLMs like GPT-3, GPT-4, and Galactica, the cost of training and fine-tuning these models has become a major concern. The authors point out that instruction tuning is a powerful way to adapt LLMs to downstream tasks, but it's expensive because of the huge data requirements. So, what's their main idea?
The core idea is to explore low training data instruction tuning, or LTD instruction tuning. They want to see if we can get away with using much less data, maybe as little as 0.5% of the original dataset, while still achieving strong performance, especially for task-specific models. That's pretty bold, isn't it?
It is. And it's a big deal because, as the paper mentions, training costs can be astronomical. For example, OpenAI's DaVinci model costs 0.03% per 1,000 tokens for instruction tuning. If you use a dataset like P3, which has 250 billion tokens, that's millions of dollars just for one round of tuning.
Exactly. So, the motivation is clear. If we can reduce the data needed, we can save a lot of money and make LLMs more accessible. The paper also discusses how most research has focused on increasing data and instruction diversity, but not much on reducing data for specialization. That's a gap they want to fill.
Right. They ask some important questions. If we only care about optimizing for a specific task, how much data do we really need? How many instruction types are necessary? And can we get away with just a handful of examples?
To answer these, they propose a method for selecting the most valuable core samples from existing data. The goal is to help the model learn what it needs for a downstream task with as little data as possible. They use a co-reset-based selection approach. Can you explain what that means?
Sure. The co-reset-based method involves several steps. First, they encode each training sample into a sentence embedding using a pre-trained language model. Then, they pre-process these embeddings with mean pooling and L2 normalization. After that, they cluster the embeddings in latent space using k-means clustering.
That's interesting. So, after clustering, they identify the center of each cluster, which represents the distribution center of the task data. Then, they use the k-center greedy algorithm to select a small set of core samples that best represent the full dataset's distribution. This subset is then used for instruction tuning.
Exactly. The idea is that by carefully selecting these core samples, the model can learn just as effectively as if it had seen the whole dataset. This is a big shift from the usual approach of just throwing more data at the problem.
The paper also provides a clear illustration of the difference between traditional fine-tuning and instruction tuning. In fine-tuning, the model predicts labels for samples, while in instruction tuning, it answers questions based on instructions. This makes instruction tuning more human-friendly and potentially more data-efficient.
That's a great point. The authors also highlight that instruction tuning can help models generalize to unseen tasks and align better with human intentions. But their focus here is on specialization, making a model really good at one specific task with minimal data.
Let's talk about the experiments. They use the Galactica 1.3b model, which is trained on scientific data and is well suited for tasks like citation prediction, question answering, and summarization. For their experiments, they use the P3 dataset, which covers tasks like natural language inference (NLI), sentence completion (SC), word sense disambiguation (WSD), and core reference resolution (CR).
Yes, and for the NLI task, they use datasets like RTE, CB, and ANLI. For SC, they use COPA, HelloSwag, and StoryClose. For CR, they use Winogrande and WSC, and for WSD, they use WIC.
They also generate instruction-style datasets by randomly selecting one prompt from each dataset. In terms of evaluation, they use a method where the model is given a tokenized sequence and answer options. The model outputs a probability for each answer, and the one with the highest probability is chosen as the model's answer. This is a standard approach for evaluating LLMs on multiple-choice tasks.
Now, let's look at the results. The most striking finding is that for the NLI task, using only 0.5% of the P3 dataset, their method achieves a 2% improvement in performance over the baseline that uses the full dataset. That's impressive, isn't it?
It really is. They also find that for task-specific models, using only relevant data for the target task and a single instruction can be more effective than using large-scale multitask models. In fact, increasing the number of instruction types has diminishing returns, and sometimes a single instruction outperforms 10 different instructions.
That's a key insight. It suggests that for specialization, less can be more. The diversity of tasks and instructions might actually hurt performance for task-specific models. This is contrary to the common belief that more data and more variety are always better.
The ablation study is also interesting. They compare their co-reset sampling method to other approaches, like selecting the most similar or least similar samples based on cosine similarity. The co-reset method outperforms the others by a wide margin. The other methods even perform worse than the vanilla model in some cases.
That's right. The authors speculate that sampling based solely on similarity can lead to imbalanced datasets, dominated by certain data sources like RTE or ANLI. The co-reset method, on the other hand, ensures a more representative and balanced subset.
The paper also discusses some limitations. Due to computational constraints, they only test their method on the Galactica 1.3b model and focus mainly on the NLI task. They acknowledge that more work is needed to validate these findings on larger models and a wider range of tasks.
Yes, and they mention that they're exploring other methods for reducing training data, but those results aren't ready yet. They plan to report on those in future papers.
Let's take a step back and think about the broader implications. If we can reliably train task-specific LLMs with just 0.5% of the data, that could democratize access to powerful AI models. Smaller organizations and researchers with limited resources could fine-tune models for their needs without breaking the bank.
Absolutely. It could also make it easier to deploy LLMs in specialized domains, like healthcare, law, or scientific research, where labeled data is scarce and expensive to obtain. By focusing on the most informative samples, we can get more bang for our buck.
Another interesting aspect is the potential for faster iteration. If you only need a tiny fraction of the data, you can experiment more quickly, try different instruction formats, and adapt to new tasks as they arise.
That's a great point. It also raises questions about the limits of this approach. For example, how small can the dataset get before performance starts to drop off? And does this method work equally well for all types of tasks, or are some tasks more amenable to low data tuning than others?
The authors suggest that their findings may be specific to the NLI task, and more research is needed to generalize to other tasks. But it's a promising start, and it challenges some of our assumptions about data requirements in LLM training.
Let's talk a bit more about the technical details. The sentence embedding step uses pre-trained models like Galactica or BERT. They extract the last hidden state for each sample, perform mean pooling, and normalize the embeddings. This creates a compact representation of each sample in vector space.
Then, they use k-means clustering to group similar samples together. The center of each cluster represents the center of the task data distribution. By finding the samples closest to these centers, they can select a small, representative subset.
The k-center greedy algorithm is key here. It selects k-center points to minimize the largest distance between any data point and its nearest center. This ensures that the selected samples cover the full diversity of the dataset as efficiently as possible.
That's right, And by using this method, they can reduce the dataset to just 0.5% of its original size without sacrificing performance. In fact, they sometimes see improvements, which suggests that the full dataset may contain redundant or even distracting information.
The evaluation results back this up. For the NLI task, the co-reset method achieves an average accuracy of 56.64%, compared to 54.06% for the full P3 dataset. That's a significant gain, especially considering the massive reduction in data.
The ablation study further supports this. The top K, least K, and mixed sampling methods all perform worse than the co-reset method, and sometimes even worse than the vanilla model. This highlights the importance of careful sample selection.
The paper also touches on related work. They mention methods like self-instruct, which generates its own instructions, and deft, which retrieves similar data using k-nearest neighbors. But these methods are more about data augmentation, while the focus here is on data reduction.
They also discuss the scaling laws for neural language models, which suggest that larger models need more data to reach their full potential. But if we can be smarter about which data we use, maybe we can bend those scaling laws a bit.
That's an exciting possibility. It could mean that the next generation of LLMs can be trained and fine-tuned more efficiently, making them more sustainable and widely available.
The authors conclude by emphasizing the need for more research. They hope their findings will inspire others to explore low-data instruction tuning and to rethink the conventional wisdom about data requirements in LLM training.
They also plan to test their method on larger models and more diverse tasks in the future. It will be interesting to see if the results hold up at scale.
Before we wrap up, let's summarize the key takeaways from this paper. First, task-specific LLMs can be effectively trained with as little as 0.5% of the original dataset, using a co-reset-based selection method.
Second, increasing the diversity of instructions and tasks doesn't always help. For specialization, a single instruction and focused data can be more effective.
Third, careful sample selection is crucial. The co-reset method outperforms other sampling strategies and can even improve performance over the full dataset.
And finally, this approach has the potential to make LLMs more accessible, efficient, and adaptable to specialized domains.
That's a great summary. This paper opens up new avenues for research and challenges some of our assumptions about LLM training. It's an exciting time to be working in this field.
Absolutely. That brings us to the end of today's episode. We hope you enjoyed this deep dive into maybe only 0.5% data is needed, a preliminary exploration of low training data instruction tuning.
If you have any questions or comments, feel free to reach out to us. And stay tuned for our next episode, where we'll review another cutting-edge paper in AI and machine learning.
Thanks for listening, everyone. To summarize, this paper shows that with smart data selection, we can train task-specific LLMs with just 0.5% of the data, sometimes even achieving better performance than using the full dataset. This could revolutionize how we approach instruction tuning and make powerful AI models more accessible to all.
Goodbye, and see you next time.